He said no extensions of the coaches.
I can leave that. No. The ones that are harder, I like. But they're not like hard. They're just not you. Oh yeah.
Right, two concepts we talked about yesterday was, first off, translations of exponential functions. When you have an exponential function, the variable is in the exponent. And we can look at graphing by looking at vertical horizontal translation. We can graph this initially and then look at a vertical translation, a horizontal translation, and be able to just shift points and not have to deal with all the points and plugging in values of x and solving for the value of y. The second concept we talked about yesterday was if x to the a is equal to x to the b. If we have two bases that are equal to each other, then their exponents must be equal to each other. So when solving problems, as you have in the bottom here, you want to try to get bases that are equal. And once you get bases that are equal, then the exponents will be equal. Solutions were provided for you. Any questions you have on any of the problems throughout the worksheet here? Once again, need to keep up with the work. Yeah?
The graph.
The graph? Which one?
Oh, the one in front. Oh, my bad. The first one.
We have the graph y equals f of x is equal to 2 to the x power. This is our original function. So what we want to do is we want to gain some points here that we can utilize. If x equals 0, 1, and 2, we would have the value of 1, 2, and the value of 4. So if I would plot my original points here, if x is 0, y is a value of 1, x is 1, y is a value of 2, x is 2, y is a value of 4. We will be asymptotic to the x-axis here. So we get our base graph that we can utilize y equals 2 to the x by just plugging in values of x, solving for y. Now if we take a look at any of the problems or any of the parts that we want to deal with here, if we take a look at problem number 1, we have f of x is equal to 2 to the x plus 1. Well, this will give us a vertical translation of a value of 1. So all of our points are going to have a vertical translation of 1. So each one of my points here will go up 1 position. My asymptote, my horizontal asymptote, will shift now to y equals 1 because we were at a horizontal asymptote at 0. So now our horizontal asymptote will go to y equals 1. So here would be our graph. If I take a look at the second part, I have a horizontal translation of positive 1. So all of my points here, I'm going to have a horizontal translation of 1 to the right. I will still have my horizontal asymptote on my x-axis. And the last one, we have a horizontal translation of -1, but then we have a reflection about the y-axis. So we're going to have a horizontal translation of -1, so we're going to go back 1, but then we're going to reflect it about the axis. So we're coming here, and then we're reflecting over to here. We are coming here, and then we're reflecting back over to here. Okay, so you're now reflecting about the x-axis or y-axis there. Other questions? We take a look at problem 6 real quick. We want to get this to be a like basis. Okay, so we have the value 9 and 27. What would be our like base for 9 and 27? 3. So we can take 3 to the second power. 9 we can write 3 to the second power. 27 we can write as 3 to the third power. So what we've now gained is we've gained our like basis. If we have a like basis, then the exponents must be equal. Well, on the right-hand side here, we have a power to a power. So this is 3 to the second is equal to 3 to the 3 times x plus 4 power. When we have a power to a power, once again, this is going to tax you back into your algebraic skills of your exponential algebraic skills. We have a power to a power, so if we have a power to a power, we multiply them. So if we have a like basis, exponents must be equal. So 2 is equal to 3, x plus 4. So that gives us an equation that we can now solve for x. Once again, have to go back to what your bases were, or what your exponents, your properties of exponents, back in Algebra 1, Algebra 2, all those that you learned back then, you're now applying them. Any other questions? All right, you will need your calculator.
Last night, at that ceremony, I was wearing a white long sleeve, and it was everything. Because the lights were off. So I wore it. But I was like inspired. A tie, white shirt. What? Why aren't you on it? On it. It's a good thing to put on a resume. Or clock applications. Yeah, we don't have a game until the next Friday. So we play tonight, and then we don't play until the next Friday. And we play Chippewa, I think. For Northwestern.
Now on the side of your calculator, on the side of your calculator on the left-hand side, you have an LOG button, which stands for a logarithm button. On the left-hand side here, you have an LOG button. I know when when I was sitting in your seats, when I was over in the hallowed halls of Orville High School, going through the math class, I didn't have a calculator. I'd always have to borrow my friend's calculator if I needed to do something real quick. But it was one of those buttons that I sat there. We never learned logarithms when I was in high school. At least I don't remember. We never learned logarithms. But I remember sitting there working with a calculator, and I knew what a square, I knew what a square root was, I knew what those values were, I knew how to take things to an exponent. Those I understood. But the log button was always a mystery to me. I would take the log of values, and I wouldn't know how it came up with the value that it did on the calculator. Did not know, did not understand the idea of logarithms. And I didn't really understand logarithms until I actually started teaching it here. But if we look at the log button on the calculator and take the value of these logs, take the log of 1, what do you get? Take the log of 10, what do you get? Take the log of 100, what do you get? Take the log of those values and write down the values that you would come up with from your calculator. And as always, what we'll do is we'll develop a pattern. Brenda, if you read down your values, what do you have? Just read down your column.
0, 4, 2, 3, 4, 5, 6, 7.
All right, so we come down to nice, even whole numbers. Okay, we come down to nice whole numbers. Now the question is, what is the relationship between the numbers we came up with and the numbers we took the log of? Connor? The number of zeros. This is 3, I have 3 zeros. This is 2, I have 2 zeros. This is 4, I have 4 zeros. Well, if we think about mathematically, how do we get zeros at the end of a number? How do we get zeros there? What can we do to add a 0 at the end of a number? If we have zeros there, we are multiplying by what value here? 10. We're multiplying by the value 10. Well, when we have logarithms, we have what is called a base, which is a subscript to the logarithm. This is a base. If I would multiply this base by the value of 2, or to the exponent of 2, or if I multiply this base 2 times by itself, I would come up with 100. If I would multiply this base times 4, or 4 times, I would come up with 10,000. It is telling us how many times we are multiplying that base by itself. I'm multiplying the value 10 by itself 6 times, because I'm going to come up with the 6 zeros there when I multiply by 10 6 times. I'm going to come up with 5 zeros when I multiply by 10 5 times. So this here, this value, this base that we have, is the value that we multiply by itself the number of times that we come up with respect to our exponent, or our value out here with respect to logarithm. Which turns us into the idea, well, if I'm looking at a value that's called a base, if you have a base, you also have what is called an exponent. You have a base, you have an exponent. Just like we have here a base of a and an exponent of x. This is an exponential form to an equation. It is something that we are fairly familiar with. If I would take 10 to the second power, we would come up with 100. We know this. If we would take 10 to the third power, we would come up with 1,000. We know what that means. We understand that aspect of mathematics. We've dealt with that aspect of mathematics throughout our algebraic career in high school, and even probably back into 8th grade math. We understand that. We are very comfortable with that. But when we throw the idea of logarithms in here, that's something that we get a little squirmish about. Because we don't really use logarithms all that much in everyday life. Okay, we don't go to the gas station and fill up our gas tank and sit there and go, okay, I'm going to use logarithms to be able to solve an equation. I have $20. How many gallons of gas am I going to be able to put into the gas tank? We don't use logarithms there. We go to the restaurant, we're paying our bill, we're figuring out a tip that we need to provide there. We're not figuring out any type of logarithm. So we don't use logarithms in common life. So we tend to be a little bit more squirmish about that, but exponents, we can handle that. But if we have a to the x power is equal to b, we can change this into a logarithmic form. And that logarithmic form would be that a to the x power is equal to b. We could change this into a logarithmic form of log base a of b will give us a value of x. Exponential form we feel comfortable with. Logarithmic form we're a little iffy about. So my suggestion always is when given a logarithm, change it back into an exponential form because we feel a little more comfortable in an exponential form than we do logarithmic form. When finding a logarithm of a value, the solution is the exponent to the base of the logarithm. So whenever you solve a log problem, your solution is going to be an exponent. Your solution is an exponent. So what I didn't realize when I was in high school and I'm sitting there playing with the calculator and I hit the log button, I would come up with these decimal values. I had no idea how I came up with those decimal values. What I was finding is I was finding an exponent to a base to come up with a value that I took the logarithm up. If you say you have an exponent, you need to have a base. You say you have an exponent, you have to have a base. Well, if I take some base to some exponent, that's equal to some value. 2 to the third power is equal to the value of 8. 5 to the fourth power is equal to 625. If I have an exponent, I must have a base. Because if I don't have a base over the next one, it's just a number. So we have base to the next one is equal to a value. In a logarithmic form, this is a log to that base of some value is equal to the exponent. Logarithms are ideas of exponents and working with exponents. When you deal with logarithms, you deal with the idea of exponents. And if you take a look on your calculator, you have your log button here. The inverse of that is 10 to the x power. It deals with that base to an exponent. We have what is called a common log, which is log base 10, which is your calculator log. When you hit your LOG button on the calculator, that is a common log, that's log base 10. And most of the time, you won't see the base 10 there. It is if you just have a log there, that is understood to be a base 10 log. That's your calculator log. We also have what is called a natural log, which is log base E. And when you have a log base E, this is your natural log, which is symbolized by ln. If you look on your calculator along the left-hand side, you also have an ln button there. And the inverse operation to the ln is e to that x power. Well, if I take the log of negative 10, if you take the log of negative 10, what do you come up with? Yeah, you get a domain error. How about 0? Domain error. But if I ask you to take the log of 0.1, can you do the log of 0.1? Yeah. You get negative 1. How about the log of 0.0001? Can you find that? Yeah, you get a value there. You get a value of negative 4. But if I take the log of 0, I have an empty set. I take the log of a negative, that's an empty set. So we cannot take logs of negative numbers, and we cannot take logs of 0. So whatever we're taking a log of has to be greater than, this value here has to be greater than the value of 0. So if I have a log of some function f of x, that f of x must be greater than the value of 0. So if I look at a problem here, log base 2, or a log of 2x minus 6, and I want to find just the domain. Just the domain. Well, that 2x minus 6 has to be greater than the value of 0. So we can add our 6 over, divide by 2. So x has to be greater than the value of 3. So we have x as a member of 3 to positive infinity. Go find your domain for the next one. Check your answer with somebody around you. So what do you have for a domain? X the member of 0 to what?
0 to 7.
Just 0 to 7? I can subtract 7, so I have negative x is greater than the value of negative 7. divide by -1. So x is going to be less than the value 7. So we have from -infinity to the value of 7. Even though we, well, let's take, what if I put in the value of -10? So we have 7 minus a -10. Minus the negative turns us into a positive, so we have log of 17 there. So even though our domain takes us into the negative world, when I subtract it, it's going to turn positive on us. Well, if I have log base 2 of 32, being able to calculate this, that's, once again, it is a foreign idea to take the log base 2 of 32 because we're not very comfortable with logs. But if we would convert this into an exponential form, I want to find a value of x. Log base 2 of 32 is equal to x. Well, let's change this into an exponential form. This is logarithmic form. What would be the exponential form? Once again, this is logarithmic. Whoops. This is logarithmic here. I want to take it here and put it back into an exponential form. I have a base, I have an exponent, I have a value. When I take a log, I'm taking a log of value, my solution is an exponent. So if I take the log, my solution is going to be an exponent. So if I rewrite this exponentially, at least what would this be? What's your base?
2.
What's your exponent? What's your exponent? We have a log of some value is equal to an exponent. Well, what's my what am I equal to? What are we equal to? Log base 2 of 32 is equal to x. What are we equal to? Now, I'll look up here. What are we equal to? X. And that's equal to what? 32. Now I'm in an exponential form. Now I feel a little bit more comfortable with this. 2 to what power gives me 32? But what's the value of x? 2 to what power? Sammy? 5. X equals 5. Or I could write this, if I wanted to, going back to what we did yesterday, 2 to the x equals 2 to the 5th power. So x equals 5. Once again, throw in a value of x. This is logarithmic form, write it as an exponential form. What's my base? What's my exponent? What's my value? Clay, what's our base, exponent, value? 7 to the x equals 49. What exponent do I take 7 to get 49? 2. This you feel comfortable with. This you feel squirmish with. Change it into an exponential form. Okay? Log base 25 of 5 equal to x. Write it exponentially. Leah, what would this be exponentially? Is equal to what? Okay, so if I take a look at this, okay, let's take a look. Write it as a like basis. Well, 25, we can write it as 5 to the 2nd power, to the x power, is equal to 5 to the 1th power. Power to a power, multiply them, If we have a like basis, the exponents must be equal. So x is equal to 1/2. Or you can think back to what exponent do we utilize when I'm taking the square root? Well, that exponent is 1/2. Once again, it's going to tax you on your properties of exponents. Rewrite it as exponential form. We have log base 2 of 1/8 is equal to x. Olivia, what would it be exponentially? 2 to the x equals 1/8. Okay, 1/8 we can write as base of 2 to the what power? Alright, this would be 2 to the negative third power. This is 1 over 2 to the third power. To bring it up top, we have to throw the negative with it. So x would equal -3. Once again, we're going to have to revive our ideas of exponents. Log base 5 of x plus 5 is equal to 2. Rewrite it as an exponential form. What's your base? What's your exponent? What's your value? What's your base? What's your exponent? What's your value? Dave, what's your base? What's your exponent? What's your value?
What? Base of 5. Exponent of x to the plus 5.
Base, exponent, value. Log of the base of the value is equal to an exponent. Whenever we solve for a log problem, it's equal to an exponent.
Okay. So it's
What?
an exponent of 2.
So we have an exponent of 2 is equal to
X plus 5.
x plus 5. So now we can simplify it. 25 is equal to x plus 5. So x is equal to value of 20. Rewrite it exponentially. What's your base? What's your exponent? What's your value? Maddie, what's your base? What's your exponent? Value? So we have 2 to the third equals 2x minus 6. 2 to the third is the value of 8. Now we have an equation to solve. We can add our 6 and divide by 2. So x equals 7. What's our base? What's our exponent? What's our value? Which gives us now a quadratic equation to solve. Solve the quadratic equation, we need to get it equal to 0. So we can add our 9 to both sides. Factoring it down. factor x plus 9, x minus 1. So x is equal to negative 9 and positive 1. Now what you need to do is you need to check. If I put negative 9 in here, do I stay positive or negative? This gives me 81 minus 72. I'm going to be positive there. If I put 1 in there, I get 1 plus 8. I stay positive. Let's solve the next one. Take it out of the exponential form into logarithmic form into an exponential form. We have a square root. What exponent can we write as a square root? 1/2. So we have 3dx is equal to 3 cubed to the 1/2 power. Power to a power, we can multiply. We have 3 halves. X equals 3 halves. You need to practice them. Once again, to get comfortable, you have to go through problems. Because logarithms are not things that we sit there and we relate to and do in everyday life and everyday mathematics. Okay, so you have to practice the idea of logarithms. We'll spend 2 days on working through worksheets like this. Today and tomorrow. We'll go over the log properties on Thursday and Friday. And that will finish up our chapter over exponents. We'll get through this real quick. Adios, have a good day. Solution proposed for you.
What do you have to do on Monday?
We'll be
Reviewing?
and a unit test Tuesday and Wednesday next week.
Okay, so I have my time to do that. Do you want me to take it Monday and Tuesday? Does that work? What do you prefer to do?
What would you prefer you do? I'm not going to tell you what you do. You do what you feel comfortable with. Is it left shoulder or right shoulder?
My left?
Okay, so you can have your writing still. If you want to do everything prior to, that is fine. And then take your test when you come back. But that following week, there's going to be a review for the final on Monday and Tuesday. And then we'll go into the final on Wednesday and Thursday.
Yeah, so I'll have that on Wednesday. I won't come back for that Thursday, Friday.
All right.
So I did exactly. I'll figure out.
You figure out what you want to do because you're going to have a unit test over exponents, and then you're going to have a final. Okay? If it was me, but you have to do what's you're comfortable with.
Yeah.
Okay? If you want to wait till you come back and do the unit test because you don't quite feel comfortable with what you're doing here, you do it after the after your surgery. If you feel comfortable doing what you're doing here, then you get it both days of your test done before you leave.
I'll
So
let you know.
you do what you feel comfortable with.